In section 11.4, we've shifted our focus from arithmetic and geometric sequences to now we're going to be talking about arithmetic series. And this first slide is really just so that you can see the difference between what we call a sequence, which is merely a list of terms that follow a particular pattern. And if it's truly arithmetic, then the pattern will be that we're adding the same number each time to get to the next term. And we call that term the common difference. So in my example here, this is a sequence where the common difference is 4. Notice that we're adding 4 each time. Well, below that, I wanted you just to see how what a series is all about. Just think of the terms in a sequence that are being added up. And that's what a series is. So a sequence is merely a list of the terms. A sequence is a list of the terms. A series is when we want to find the sum of those terms. And as you can see, there are really two types. This is a finite. Finite just means it ends. You can see that we have a definite ending term. So we will be able to find the sum of these finite series. But if the sequence or the series is infinite, as you can see here, there's no way that we could ever get to a point where we could find the sum of this particular series. So our focus in this lesson will obviously be dealing with finite arithmetic series and how to find the sum of these series. So just wanted you to see the difference. When you see the word sequence, it means just the list. Series, the sum of the terms in the list. All right, so we can skip this slide. Problems 8 through 12, 37, and 40 are going to be asking you to do something like this. They're going to describe a particular sequence, and I've got a couple here at the bottom of this screen. Two things that they want us to do. They first of all want us to evaluate the series, okay, which is, in other words, when you see the word evaluate a series, you can always think of, that just means find the sum of this particular series. So I want you, in order to find the sum of an arithmetic series, here is another formula that I want you to practice during this lesson so it will become very familiar to you. This big capital S stands for sum. This means how many terms are we going to be adding. Here we have that same number in this numerator, number of terms, always divided by 2. And that's going to be multiplied times, in the parentheses, the first term plus the last term. So I'm going to show you how this formula would be applied in this set of homework problems. All right, so we're told that this sequence, even though we don't see all 8 terms, we see enough of the pattern to tell, obviously, the first and the last, and we know that it's arithmetic. So knowing that there's 8 terms here, let's do the sum of these 8 terms. Will be found by doing the number of terms divided by 2. And then inside the parentheses, we'll do the first term, which we see as 1/2, plus the last term, which we can see as 15/2. Okay, so in the parentheses, this would just be 16 over 2, which is 8. And outside the parentheses, 8 over 2, which is 4. So really all we're doing is multiplying 4 times 8. And the sum of these 8 terms that are being described in this sequence would be 32. And that would be my answer if this were a homework problem. Okay, let's take a look at letter B. Another sequence of 8 terms. Well, if this were a series, which means we would be adding all these up, what would the sum of this series be? All right, so once again, the sum of 8 terms, 8 divided by 2. In the parentheses, we're going to do 1765. That's the first term, plus the last term, which is negative 6 92. All right, so if you need to grab a calculator, we'll do the parentheses 1765, and you can basically do minus 692, and that number times 4 is 4,292, so that would be the answer for the sum of that series. Okay, so make sure you show this formula. It's going to help because you will need to know it for upcoming quizzes and tests, and make sure you show it for these problems that are related. Okay, now let's talk about summation notation. The short definition of what summation notation is, I have it here in blue. Just think of a shorthand or a very abbreviated way to write an entire series. Okay, and I have an example here for you. Here's a series, 2 plus 6 plus 10. You can see it's arithmetic because we have a common difference of 4. We're adding 4 each time. And the way I would represent this particular series, this long list of terms that are being added up, is by using summation notation. And here's an example of it. Now you might be thinking, well, that's kind of just for 8 terms, why don't you just list them all out? And I would agree, for 8 terms, it's hardly worth the effort to come up with summation notation, but sometimes we're dealing with 1,000 terms. And instead of listing out all 1,000 terms and show that they're going to be added up to come up with a sum, we can just do a condensed version of that entire series by using what we call summation notation. Notice that it involves this capital letter sigma, and the rest of this lesson, or a big part of this lesson, is how do we come up with this expression to the right of sigma. Okay, I just wanted you to see this and how it relates to this series. For example, let's just take this bottom number 1 and use that as an input. If we put 1 in for n and do the math, we get 4 times 1 minus 2. Well, what we found here is the first term, which is 2. 4 minus 2 is 2. You can't see my number over here. It's kind of chopped off, but the last number of this series is 30. Well, to get the last number of summation notation, I'll just take the top number of above sigma, plug it in for n, and 4 times 8 is 32, minus 2 is 30. And then we can come up with all the terms in between. If I wanted to find the second term, for example, I would let n be 2. 4 times 2 is 8, minus 2 is 6. That's the second term. So you can see how all of these are really captured in this one expression. If we want to know a particular term in the list, we just plug that number in for n. And if we want to know the whole sum of the series, then we can use our formula that we just learned. Okay, so let's go through some examples. 14 through 18 are going to be like this. They're going to use the words use summation notation to write the series. Okay, and when you see summation notation, just remember that's going to involve sigma. Okay, and I'm going to walk you through the process of how to come up with that complete expression, the summation notation, to represent a given series. Well, the first step is going back to a formula that we used back in section 11.2. We used this formula to, anytime we wanted to find, say, the 11th term of an arithmetic sequence, we just made n become 11. We had to know what the first term was. We had to calculate what the common difference was, plug all those numbers in, and we could have found the 11th term. Well, that is a good use of this formula, but it's also used for something else. we can use this formula to help us come up with that expression that falls to the right of sigma, this 4n minus 2 in parentheses. The way we find out what that is by using this formula. Okay, let me show you. So we really, since we're not looking for an nth term of a sequence, I'm just going to take that off. We don't really need that part for this particular problem. So let's plug in our first term, which is 2. I'm not putting anything in for n, okay? That's not the purpose. I do need to, however, substitute a number in for d, and the common difference, notice that to go from 2 to 4 to 6, we're adding 2 each time, so d is 2. All right, now I'm going to simplify this by using the distributive property. I'm going to distribute 2 to both of these terms in the parentheses. 2 plus 2n minus 2. And then we can cancel these, and all that's left is 2n. So what I've just found, and we'll finish it all up in just a moment, what I've found at this point is this expression that would go to the right of sigma. Okay, so here we go. We're going to finalize our answer. Let's see, we were told that there's 10 terms. We're summing. They got us started with this series, but they're telling us without showing the whole series that there's a total of 10 terms. All right, so that means at the top of sigma, I'm going to put 10. That's how many terms. And I'm going to start adding with the first term. So when you're writing summation notation yourself from scratch, as it were, you will always put n equals 1 as the bottom limit of sigma, and then how many terms you're adding through as the top. And then our previous step, our previous slide, I'm going to skip that slide, we found 2n as the expression to the right of sigma, and so that would be the final answer. If this were a homework problem, write summation notation for this particular series through the 10th term, then my answer to that would be here. Okay, let's try another one. You'll be doing this again, 13 through 18. Here's a series, or at least the beginning of a series, but this time we're told to write summation notation that would represent how to come up with the sum of all 50 of those terms in this series. Okay, so I went ahead and wrote sigma out. N equals 1 will be on the bottom. This time 50 will be on the top. And I showed you again that formula that you will use to come up with this expression. All right, so first term, 8 plus n minus 1. And then the common difference, this time we're adding 8 each time. All right, distribute 8 plus 8n minus 8. And once again, those constants will cancel each other. And so the expression that goes to the right of sigma will just be 8n. Now, I don't want you to think that it always happens that these constants will cancel. Let me just give you a for instance. Let's just pretend for a second. I know it doesn't match up, so don't take what I'm doing here as it goes with this, but I just want to use this as a sample. What if I had this? Okay, and that means I'll erase this. Okay, so we still distributed, but this time we have 5 plus 8n minus 8. Well, now we simplify, we get 8n minus 3. Okay, now I know it doesn't match, but just bear with me for a second. If we happen to end up with an answer for this expression like this, then it is vitally important when you have a binomial expression like this to the right of sigma, and this will happen in your homework, you must enclose that binomial in parentheses. Okay, for monomials, like we've come up with in our two examples, not necessary to have parentheses, but for binomial expressions like this, it matters. So try to remember to enclose binomials like this with parentheses. Okay, but I'll go back and put that at our final answer at the way we had it before. All right, I hope that makes sense. So that was 8, that was 8, and we just had 8 in, so since it's a monomial, we do not need parentheses. Okay, and this is going to wrap it up for us. When you get to this block of problems, they're going to give you a series that is represented by summation notation, and they want you to come up with some answers. All right, there's basically 4 answers here. So first of all, let's find how many terms are in this series. Well, it says to start with the first term and go all the way down to the 4th term, and that's obviously 4 terms. So my answer for part A, the number of terms in this series, would be 4. To find the first term, anytime you want to find the first term of summation notation, just take the bottom number and plug it in for n. Just think inputs and outputs. If I input 1 in for n here, I get -2 plus 3, which is 1, so the first term is 1. And if I want to find the last term of this series that is in summation notation, I take the top number, sigma, and I plug it in and see what comes out. So -2 times 4 is -8. -8 plus 3 is -5. So that's the last term. And now to evaluate a series, that's just, again, another way of saying find the sum of the series. I want you to go back and use that formula that we dealt with early on in this lesson. Number of terms divided by 2 times the first term plus the last term. Okay? So we have this formula, and you can see how we use it to come up with the sum of these 4 terms in this series. So let me just give you a word of caution that this tends to give people a little bit of trouble. I'm going to change this problem just a little bit, and I think one of your homework problems will deal with this, and you'll see it also on your test. Let's just take this same summation notation expression, but this time I'm going to let the bottom number say n equals 6. And let's just say the top number is 17. Okay, so what I'm really doing here is I'm helping you out with situations like this when it comes to answer letters A and B. Some people mistakenly, when they want to find the number of terms looking at summation notation, they just look at the top number and they write down that as their answer. Well, you got to be careful, because the bottom number affects the number of terms as well. Okay, let's just think of it this way. I'm just going to list 17 numbers just real quickly. Okay, let's just pretend for a second that we have these 17 numbers that are in a series. Okay, so they would be all added up. Well, the way this is worded, the way this is given to us is they want to find the sum starting with n is 6. Remember earlier we said we identify terms like a sub n, and if I change this to the 6th term, that literally means the 6th term in a list. Well, that's what this is talking about. So if n is 6, what it means is I'm actually starting my sum with the 6th term. And I'm going to keep on adding until I get to the end of this series. Okay, so how many terms is that? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if this were your problem as a homework that you had to do, then my number of terms would not be 17. It would actually be 12. So I showed the class another way of doing that, and this always works. If you want to just take the top number, the upper limit is what we call it, of sigma, and subtract the bottom, and then always, just don't forget, you always want to do plus 1. And that will get you the number of terms. Now, yes, if the bottom number says n equals 1, then your number of terms will be whatever this upper number is. But you have to be careful when it's something else. Like in this case, I just changed it to 7. Well, now my number of terms will be 17 minus 7 plus 1, which would be 11. Okay? So please watch out for that. We have people that make mistakes in that area. And then I'll put this back to 6. With n equals 6, it also affects how I find the first term. Some people have the idea that if they want to find the first term, they always plug 1 in for n. Well, that's not true. In summation notation, if you want to find the first term that is part of your sum, you take whatever the bottom number is and you plug that in for n. So if I change this to n equals 6 and I want to find the first term, then I let n become 6. And then I simplify negative 12 plus 3, and so my answer would be negative 9. Okay, so I just want to give you a heads up because those are two areas excuse me, that cause people a little bit of trouble. Pay attention to this bottom number. Not only will that affect your number of terms, but it will also affect how you find the first term. Find the first term, you just, whatever this number is on the bottom, you plug it in, see what comes out, and that will be your first term. Okay, I have the assignment there on RenWeb, so let me know if you have any questions.